Plastic is everywhere. It's in the deepest parts of the ocean, in the food you eat, in the water you drink. Scientists have even found microplastics in human brains and bloodstreams. We produce over 400 million tons of plastic every year. And here's the problem. Only about 9% of it ever gets recycled. The rest? Landfills, incinerators, our oceans, our bodies. But in July 2025, researchers at Yale University announced something remarkable. A breakthrough that could turn plastic waste into fuel efficiently, cheaply, and without the expensive catalysts that have held this technology back for decades. It sounds like the solution we've been waiting for. But is it? Or is this just another way for the fossil fuel industry to keep us dependent on petroleum? Plastic to fuel, breakthrough, or greenwashing? To understand why this breakthrough matters, we need to understand the scale of our plastic problem. Since the 1950s, humans have produced over 9 billion tons of plastic. That's more than a ton for every person alive today. And production is accelerating. We now make more plastic in a single decade than we did in the entire 20th century. Of all the plastic ever made, 79% sits in landfills or pollutes the environment. 12% has been incinerated, releasing toxic chemicals into the air. Only 9% has been recycled, and most of that can only be recycled once or twice before it degrades. The consequences are devastating. Plastic takes hundreds of years to break down. In the meantime, it fragments into microplastics that contaminate every ecosystem on Earth. Marine animals mistake it for food. It leaches toxic chemicals into soil and water. And increasingly, it's affecting human health. Microplastics have been found in human lungs, livers, and even placentas. We're still learning what this means for our long-term health, but early research suggests links to inflammation, hormonal disruption, and cellular damage. Traditional recycling helps, but it has limits. It only works for certain types of plastic, mainly numbers 1 and 2, like water bottles and milk jugs. Everything else, plastic films, food pouches, foam containers, can't be mechanically recycled. That's where chemical recycling comes in. And that's where Yale's breakthrough enters the picture. To understand what Yale researchers accomplished, you need to understand pyrolysis. Plastic is made of long chains of molecules called polymers. These chains are incredibly stable. That's why plastic lasts so long. But that stability also makes plastic hard to break down and recycle. Pyrolysis is a process that uses extreme heat, around 900 degrees Celsius, in an environment with no oxygen. Without oxygen, the plastic can't burn. Instead, the heat causes those long molecular chains to shake apart, breaking down into smaller hydrocarbons. The result? A type of oil chemically similar to the petroleum that plastic was originally made from. In theory, this oil can be used to make new plastic, creating a circular economy. Or it can be refined into fuel. The concept isn't new. Companies have been experimenting with pyrolysis for decades. But there's always been a catch. Traditional pyrolysis requires expensive catalysts, special materials that speed up chemical reactions. These catalysts are costly to produce and don't last forever. They degrade over time, reducing efficiency and requiring constant replacement. Without catalysts, the process becomes inefficient. You get something called coking, a buildup of carbon residue that clogs the system. Temperature control becomes difficult, and the yield, the percentage of plastic that actually converts into usable products, drops significantly. That's the problem Yale researchers set out to solve, and their solution is ingenious. The research team was led by professors Lian Bing Hu and Xu Hu at Yale School of Engineering. Their breakthrough was published in Nature Chemical Engineering in July 2025, and it's a game changer. They designed a 3D printed carbon reactor with a hierarchical pore structure. Think of it like a series of filters, each one smaller than the last. The first section has pores 1 millimeter wide. The next section, 500 micrometers. The final section, just 200 nanometers. As plastic molecules break down and move through the reactor, this structure controls their journey. Larger molecules can't advance until they've been adequately broken down. This prevents them from escaping the reactor before they're fully converted. It's like a quality control system built into the reactor itself. The porous structure also helps control temperature distribution throughout the reactor. This prevents hot spots that cause coking and other problems that reduce efficiency. The results? a record-high yield of nearly 66% of plastic waste converted into usable chemicals. That's without any catalysts. To prove the concept could scale, the team also tested a design using commercially available carbon felt, materials you can buy today. Even without the precision of 3D printing, this version still achieved a 56% yield. Compare that to traditional catalyst-free pyrolysis, which typically yields 30 to 40%, and you can see why this is significant. Professor Liang Bing, who said the breakthrough offers a practical strategy for converting plastic waste into valuable materials. Professor Xu, who called the results very promising for real-world application. In an ideal scenario, this technology could create true circularity in plastic production. Plastic waste that currently sits in landfills or pollutes the environment could be collected and converted back into the raw materials needed to make new plastic. No new petroleum extraction required. And unlike mechanical recycling, pyrolysis can handle the plastics that traditional recycling can't, those marked with numbers 3 through 7. Plastic films, juice pouches, foam containers, all the stuff that currently has nowhere to go. The American Chemistry Council claims that advanced recycling reduces greenhouse gas emissions by 43% compared to incinerating plastic waste made from virgin resources. The market is responding. The global advanced recycling industry is projected to grow from $270 million in 2022 to over $9 billion by 2031. That's 32% growth every single year. Major players are getting involved. ExxonMobil announced plans for pyrolysis facilities in Texas, Louisiana, and Illinois. Chevron Phillips received a patent for its proprietary process. Startups like Brightmark are building commercial-scale plants. Bob Powell, founder of Brightmark, says his goal is 100% circularity, plastic to plastic, and that even in the interim, converting plastic waste to fuel is better than letting it accumulate in the environment. But not everyone agrees. And that's where the controversy begins. Here's the uncomfortable truth. Most pyrolysis oil doesn't get turned back into plastic. It gets turned into fuel. An analysis by the Minderoo Foundation found that of the roughly 2 million tons of advanced recycling capacity scheduled to come online over the next 5 years, less than 500,000 tons will actually be recycled back into plastic goods. The rest? It's destined to power airplanes, trucks, and other heavy transportation. In other words, it gets burned as fuel. Veena Singla, a senior scientist at the Natural Resources Defense Council, says this isn't recycling at all. If you're taking plastic and burning it as fuel, it's not feeding back into plastic production. And so to keep making plastic, you have to keep extracting fossil fuel. Then there's the energy problem. Researchers at the National Renewable Energy Laboratory analyzed the energy it takes to produce pyrolysis oil versus the energy that oil generates when burned. Their preliminary findings: creating pyrolysis oil from used plastic generates higher greenhouse gas emissions than extracting new crude oil from the ground. The process of superheating the reactor to 900 degrees Celsius requires massive amounts of energy. But perhaps the most disturbing finding involves human health. A ProPublica investigation uncovered EPA data showing that long-term exposure to emissions from producing jet fuel from plastic-based oil carries a 1 in 4 lifetime cancer risk. Linda Birnbaum, former head of the National Institute of Environmental Health Sciences, called that level of risk obscene. And who lives near these refineries? Predominantly Black, brown, and low-income communities, the same populations already bearing the brunt of environmental pollution. There's also the issue of transparency. ProPublica's investigation revealed that the industry uses mathematical accounting tricks called mass balance to inflate recycled content claims. Products labeled as 30% recycled may physically contain as little as 2 to 5% recycled material. The rest is a counting sleight of hand that shifts recycled credits from one product to another. 24 U.S. states have passed laws classifying pyrolysis as manufacturing instead of waste disposal, allowing these facilities to operate under lighter environmental regulations. So where does that leave us? Proponents argue that even if pyrolysis oil becomes fuel in the short term, it's still better than letting plastic accumulate in landfills and oceans. They point to the technology's ability to handle plastics that can't be mechanically recycled, and they emphasize that the goal is eventual circularity. Critics counter that calling this recycling is misleading. They argue it perpetuates fossil fuel dependence, requires massive energy inputs, creates toxic emissions in vulnerable communities, and distracts from the real solution, producing less plastic in the first place. Taylor Yuckert from Yale puts it this way: plastic is not an infinitely renewable resource. If you're turning plastic back into oil for fuel, you need to be comparing it to the environmental impacts of creating that fuel from fossil sources. Senator Jeff Merkley of Oregon says, the fossil gas industry is seeking to use plastics as a way to expand their production, even as they are contributing enormously to climate chaos. Both sides raise valid points. The question is, which concerns should weigh more heavily? Yale's breakthrough is scientifically impressive. A catalyst-free pyrolysis process with record-high yields could revolutionize how we handle plastic waste. But the gap between laboratory innovation and real-world impact is enormous. The technology exists. The question is, will it be used to create true circularity, or will it become another way to perpetuate our dependence on fossil fuels? The answer depends on regulation, transparency, and whether we're willing to confront the uncomfortable truth. The best solution to plastic pollution isn't better recycling. It's making less plastic in the first place. What do you think? Is this a breakthrough worth pursuing, or a distraction from the real problem? Let us know in the comments.